talking about proofs first, and then we'll do the quiz so that you can leave as soon as you're done and you don't have to wait for other people. Okay, so remember, last time we were looking at direct proofs. We're almost done with them. Let me just show you. So remember that the way a direct proof goes, okay, if you're trying to prove like P implies Q, okay, P is your hypothesis, Q is your conclusion. You start by assuming the hypothesis is true, so whatever is here, you start by assuming P is true. And then optionally, if you would like to, you know, give the reader a heads up and say, we will try to show that Q is true. Okay. And then you use definitions, theorems, etc. to make valid arguments, valid conclusions. Essentially, we're pretty much always using modus ponens. We don't say it all the time, but that's what we're doing. Until you can validly conclude the conclusion, and then you're done. Okay, so that's how they go. We have a couple more of these to do. And then we're going to look at other kinds of proofs besides direct proofs. Okay, so we've got 2 more direct proofs to do. Okay, so this time would like to prove that if x is a real number such that x is less than or equal to 2, then we can guarantee that x squared minus 7x plus 10 is greater than or equal to 0. Okay, and so notice this is a universal statement. This would be, like if we had to write this out, it would be for all, okay, x is x in the set of real numbers, if this, then that. Like that's how it would be set up if you were to write it out as a logic statement. Okay, so this is our hypothesis. And this is our conclusion. And of course, x being a real number, I guess, is part of the hypothesis. It's really the domain. But, okay, and so in a direct proof, we know, okay, that we always start by assuming that the hypothesis is true. So we're going to say, suppose x is a real number such that, that's the abbreviation for such that, so if you want to write it short like that, feel free. Okay, such that x is less than or equal to 2. And then we will show that x squared minus 7x plus 10 is greater than or equal to 0. Now, if you look at that expression and you want to show that this thing is greater than 0, do you have a gut feeling that says what you might want to do with that expression? Factor it. Like, you're probably going to want to factor it. Okay, so I'm going to put here, or equivalently, that, and then if we factor this, what is it going to factor into? X minus 5 and x minus 2. Okay, so that's just another way of saying the same thing. But if we think about it as x minus 5 times x minus 2 is greater than or equal to 0, that's going to help us with this proof. Okay. Okay, so now here we have this x minus 2. Like that's the thing that we know. We usually have to start with there. And if you look at that, that seems to be very, related to this x minus 2 down here. So since x is less than or equal to 2, okay, if we subtract 2 from both sides of this, we're going to have x minus 2 is less than or equal to 0. So now we know something about this factor right here. It is a non-positive number. Okay, so this factor. So we know something about this factor. It would be nice if we could know something about this factor, x minus 5. So, is there any argument that we could make about x minus 5? How is x minus 5 related to x minus 2? Could we guarantee that it's either bigger, smaller, whatever? It's got to be smaller. Right. Okay. So we know x minus 5 is less than x minus 2. Okay. So x minus 5 has to be less than or equal to 0 as well, because x minus 2 is less than or equal to 0, right? I can even put that in here. Okay. So now we have this, that x is non-positive, x minus 2 is non-positive, and x minus 5 is non-positive. Okay. So since the product of two non-positive numbers is what? Is it positive? It's non-negative. Yeah, it's non-negative. Okay, because non-positive means there could be a 0 in there, right? So, and you take two non-positive numbers, okay, and you multiply them together. That might be a negative number times a negative number, in which case you would get positive, or it could be a negative number times 0, because 0 is still non-positive. So we just can only say non-negative. We can't say positive. Okay, so since the product of two non-positive numbers is non-negative, we can conclude that x minus 5 times x minus 2, okay, is non-negative, right? And non-negative means that it's greater than or equal to 0. And that's exactly what we were hoping to find. So we are done. So probably one of the tricky things in here is the uses of the word non-positive and non-negative. So remember when we talked about in section 4.1 that the opposite of positive is not negative. The opposite of positive is non-positive. The opposite of negative is non-negative. And so you have to be careful about those words, but that's good. Okay. All right, so that does that one, and we've got one more. All right. And I don't think that we've done one with the divides. So this will be a good example of doing a proof with the divides. Okay. So if x, y, and z are integers such that x divides the sum of y and z, and x also divides y, then we know x has to divide z as well. So that's what we're going to prove. Okay, so notice these are going to be our hypotheses, and this is our conclusion. So it's always good to just keep track of that in your mind when you write a proof, because all of these you have to know where the hypothesis goes and what to do with the conclusion. Okay, so with a direct proof, we're always going to start, okay, by assuming our hypotheses. So we have to have x, y, and z. We're going to be arbitrary integers. So let x, y, z be arbitrary integers. Such that, okay, x divides y plus z, and x divides y. Okay. And then we will show that x divides z. Again, that statement is kind of, okay, if you read proofs, not everybody puts those in there, but it is a nice reminder to you and the person reading it that as soon as I see this, I know I'm done. Okay. All right, so that's kind of our general setup. Assume the hypothesis, say what we're going to show. Okay, and then we go to anything in the hypothesis and say, all right, well, how can we apply theorems or definitions to that? Okay, well, we know that x divides y plus z. We know x divides y. We have definitions for that, so we should be able to apply the definition to those and rewrite those in a certain way. Okay, so we know that there exist integers, let's call them m and n, such that, okay, so we'll use m for the definition that x divides y plus z, and we'll use n for the definition that x divides y. Okay, so first of all, what does it mean that x divides y plus z? Yeah, so what does that mean? Like, but what's the definition of that something, how do I know when something divides something else? Yeah, so I can take y plus z and I can write that as a multiple of x, right? Okay, so I know that I can take y plus z and I can write that as some integer, which we're going to call it m, times x. That's what it means for x to divide y plus z. That y plus z over here is some multiple of x. So that when I take y plus z and I divide it by x, I'll get an integer value with no remainder. Okay, so that would get an integer value m with no remainder when I divide that. All right, so that's what it means for x to divide y plus z. And then we can use n in our definition for x divides y. So here I can take y, and that has to be some multiple. This time I'm going to use n. And sometimes when you have multiple equations, I like to number them. I'm going to number these ones, okay, so that we can easily talk about them. So we could say, okay, substituting equation 2 into equation 1 gives, okay, so we can substitute this n plus x in for y in the first equation. So instead of y there, we'd write n plus x. We'd have n plus x plus z equals mx. Thank you. N times x. I knew that looked wrong. In my mind, I was like, that's not going to work out. What did I do? And then you told me. Thank you. Yeah, so n times x plus z equals mx. Okay, and so then if we isolate z and move everything over to the other side, I'll have mx minus nx. And then if I factor out the x, I'll have m minus n times x. Now this is good because what we were hoping to show is that x divides z. And really, to show that x divides z, we have to show that z can be written as a multiple of x. So if we look over here, we've done that. We've written z as a multiple of x. So as long as we can show that m minus n is an integer, then we have that it's an integer multiple of x. So that's the only other thing that we have to do, is guarantee that m minus n is indeed an integer. And is it? Yes. Okay, so I'll say because the set of integers is closed under subtraction, we know that m minus n has to be an integer. So by definition, x divides z. And we're done. So, we've had lots of examples of direct proofs. We did with divides, we did with even, we did stuff with greater than, less than. What was our other example? Rational numbers. Okay, so we've pretty much covered most of the kinds of things that you'll see with direct proofs. Okay, so I think if you go through all of those examples and try any other ones, you can kind of match them up to ones that we've done, and you have kind of like a direct proof recipe for any of those kinds of things. Yes?
Is there some sort of method you have to like remember all these different things that we can assume are true, or seeing those a list of things? But like,
It's not very many things.
okay.
So it's the closure properties of integers. It's anything from algebra. It's that you can always find consecutive integers, and that the relationship between numbers can be assumed. Like if you see, like here where we had like x minus 5, is it less than x minus 2? We're allowed to, because you're subtracting 5, which is a larger number than 2, like you're allowed to do those less than and greater, those relationships. Those are the only things.
Okay.
So it's a pretty short list, so hopefully it's not too hard to memorize. The issue is anything from algebra, you just have to remember algebra. So that's, I think that's the trick there. Somebody was saying the other day, oh, all those fractions, yeah, so. But anything from algebra you're allowed to use, so. If you remember your algebra, you'll probably be happier than if you don't. All right, so we are now done with direct proofs, and we're going on to proof by contrapositive. Now, the good thing is that these don't really feel too much different than direct proofs, because there's almost sort of a direct proof hidden in there. So proof by contrapositive looks like this. So remember that if we have an implication, like hypothesis implies conclusion, that's logically equivalent to its contrapositive. So anywhere I want to prove an implication, I could equivalently prove its contrapositive, and if this is true, this has to be true. And that's what proof by contrapositive does. Instead of going after the original statement of the theorem, hypothesis implies conclusion, we're going to go after the contrapositive. The negation of the conclusion implies a negation of the hypothesis. If we can prove that this is true, then by logical equivalence, we get that the original statement, H implies C, is true. Okay, and so a proof by contrapositive is essentially a direct proof of the contrapositive. Okay, so you're trying to prove H implies C, but to do it, you're going to start by assuming that not C is true. Okay, and then use a valid argument to conclude that not H is true. And if you think about that, that's just the steps for a direct proof of not C implies not H. You start with this as your hypothesis and arrive at not H as your conclusion. Okay, so it'll feel very much like a direct proof once we get, to assume this and prove this. All the rest of it will feel just like a direct proof. Okay, so let's do some examples of this. So for every integer n, if n squared is odd, then n is odd. Okay, so let's write this out. So this would be for all n over integer.
Thank you.
Okay, so n squared is odd implies n is odd. So that's the original statement. Okay. So this statement is logically equivalent to its contrapositive. So what is the contrapositive? N is even implies n squared is even. And hopefully when you look at that, you can say to yourself, yeah, it seems like this one would be easier to prove than this one. Okay, so if I know something about n, it's a little easier to argue something about n squared than if I know something about n squared and to try to argue something about n, because I got to take square roots and things. It's just a little bit harder to do. It's not necessarily impossible, but it's much harder, and this one is much easier. Okay, so hopefully you can see why hey, proof by contrapositive is desirable in this particular instance. Okay, so we might say something like clue in the reader that's reading our proof that we're actually using a proof by contrapositive. So we could say we will use a proof by contrapositive. Okay, and then maybe explain to them what that means. So something like that is, okay, we will show that if n is even, then n squared is even. Okay. And now the person reading our proof knows exactly what we're going to do. Okay. And at this point, we've got the statement of the contrapositive here, and we essentially just proceed like it's a direct proof of this contrapositive. So this is the hypothesis that we want to assert here, that n is even. Okay. So we say let n be an arbitrary even integer. And we've been here before. We know when we see n as an arbitrary integer, what's the very next thing you want to say? That there, so what is it? Yeah, so there, okay, so then there exists an integer, so you called it x, sure we'll use x, such that n equals 2x. We know n is even, and so there's got to be an integer so that n is a multiple of 2. Okay. So then we want to make an argument about n squared, right? So n squared equals, and then we have this 2x, and we would have to square that, which would be 4x squared. Okay. And how should we rewrite that so that we can show that n squared is even? Yeah. Yeah, so put 2 times, and then, so if we factor a 2 out of this, then we'll just have 2x squared left. Okay, so once we've written it as a multiple of 2, all we need to do now is just show that whatever we're multiplying by 2 is actually an integer. Okay, so is 2x squared an integer? Yeah, it's got to be, because it's only multiplication is involved, 2 and the integer x and the integer x. Okay, so because the set of integers is closed under multiplication, okay, we know that 2x squared has to be an integer. Thus, by definition, n squared is even. And that's what we were hoping, right? We said we would show that if n was even, then n squared is even. I've showed that n squared is even. There it is. So I know I'm done. So it feels like a direct proof, right? It's not that much different. It's just that we proved the contrapositive instead of the original statement. So my claim is that if you can write a direct proof, you can write a proof by contrapositive, because really they're very similar. Okay. So let's try another one of these. It's always good to, well, I tried to pick out some that would be all the different kinds of options. So we had one with odd. This time we have something with divisibility. All right, so for every integer n, if n squared is not divisible by 4, then n is odd. Okay, so if we were to write this one out, we have for all n, if n squared, is not divisible by 4, so if 4 doesn't divide n squared, then n is odd. So that's our original statement. So we would like to rewrite that as the contrapositive. So this is the original. Let's look at the contrapositive. Okay, so how would we write the contrapositive of that? N is odd? N is even. Then 4 divides n squared. Okay. So if you look at those two statements, okay, hopefully you can see that it, here we have a definition for what it means for x to divide y. We have a nice definition for that. Okay, when we go to the opposite of that, 4 does not divide n, and you have to prove there does not exist an integer such, and that's a much harder thing to do than to prove that there does exist an integer such that n squared is equal to 4 times, a multiple of 4. Okay, so once again, when we look at the contrapositive, this one looks like it's going to be much easier to prove than the original statement. So hopefully you can see why a proof by contrapositive is a desirable thing here, because this is just easier to work with. Okay, so essentially now we just need to do a direct proof of the contrapositive. Okay, so our proof, again, we're just going to tell the reader that we're doing a proof by contrapositive and what that means. So we use a proof by contrapositive. And then maybe just explain that. That is, we will show that if n is even, then 4 divides n squared. So that's what we're shooting for. So at this point, it's really just a direct proof of that statement. So our hypothesis for this contrapositive statement here is that n is even. So let n be an arbitrary even integer. And we know exactly what we're going to do. There has to exist a k such that n equals 2 times k, right? Then there exists an integer k such that n is 2 times k. That's the definition of even. So n is even, there's got to be a k that makes that true. Okay. And now, once we know that, we need to make a connection between this statement and this statement. So we're hoping to get something about n squared. Okay. So we need to think about n squared. So n squared is equal to this 2k squared, which equals 4k squared. So do we have enough to prove that n squared can be divided by 4? Yeah. Basically, like what's the only other thing we need to do? Not really. I need to just say something about what k squared is. We just have to say it's an integer, okay? Which is pretty easy. Okay, so we already know that k is an integer, so k squared only involves multiplication. So because the set of integers is closed under multiplication, we know that k squared has to be an integer. Okay. And so we now have n squared written as 4 times an integer, and we've met the definition of divides. So thus, by definition, 4 divides n squared. And I know it's easy to want to jump straight from here to here, but the definition does indeed say that this has to be an integer, so we have to put that statement in there. I know it's tempting to just skip over that, but we can't. All right. So this one, for every pair of integers x and y, if the product x times y is even, then x is even or y is even. Okay, so this is for all x and for all y. If xy is even, then x is even or y is even. So that's the original statement. So let's think about the contrapositive and why that might be a desirable thing. So first of all, what would the contrapositive be? Yeah, x is odd or y is odd. And we have to use De Morgan, right? I'm going to write this out just so it's really clear. If we did not x is even or y is even, then not xy is even, right? So the contrapositive, we, negate and swap the hypothesis and conclusion, right? And then if we apply De Morgan, not x is even is x is odd, and this or is going to turn into an and. That's very important. And then this would be y is odd. So be really careful about that. And then this would be xy is odd. Okay, so this one on the bottom would be our final statement of the contrapositive. And notice, again, this is kind of desirable. So when I have an and in here, that I can assert that both of these things are true at the same time. And then I can use both of those facts to derive something about the product. Okay. Whereas in my original statement, I would have something that I know about the product, and then I would have to conclude that either this, or both of them are true. And so trying to make an argue about this one, or possibly both of them, that's much harder than here, where I know these two things have to be true at the same time, and then I'm going to conclude that this one thing is true. Much easier to do. Yes?
So when we're doing the contrapositive, and when negating, obviously, it doesn't apply to the quantifier, it doesn't apply to the universal.
Right, I'm just replacing this statement with its logical equivalence. Yeah.
Even though you negate it, it's not negated from the
Right, I'm just replacing this part of it. Now, if I wanted to do something kind of fancy and try to pull the negation out so I could turn it into an existence or something, I could do that, but I'm probably not going to do that. I'm just going to leave it that way. Yeah. I'm just going to replace the original with its contrapositive and don't mess with the quantifiers. Okay. All right, so this is a statement we're going to go with, and it looks definitely more desirable than the original one. Okay, so here's our proof. So once again, we're just going to alert the reader, hey, we're doing a proof by contrapositive. So we use a proof by contrapositive. Okay, and then probably just tell them what you mean by that so everyone is clear. Especially on this one, like if the reader isn't really good with their De Morgan, they might not recognize what that contrapositive is. So it's good to just tell the reader. Okay, so that is, we show that if x is odd and y is odd, then the product of x and y is odd. And then, basically, we're just doing a direct proof, right? Except that this is our hypothesis, that x is odd and y is odd. So we have to say, let x and y be arbitrary odd integers. I've done quite a few of these proofs with even. We haven't done them with odd yet, but kind of the same kind of thing. We know then there exist integers, we'll call them m and n, I guess, such that, okay, so x is what? What's odd mean? Yeah, 2k plus 1, so we're going to use m for that one. So this is going to be 2m plus 1, and then y is going to be 2n plus 1. We know they're odd, so these integers have to exist to meet the definition of odd. Okay, so now we want to make an argument about the product. So if we look at x times y, then we can substitute our values, and that's going to be 2m plus 1 times 2n plus 1. All right, so if I multiply that out, I'm going to get 4mn plus 2m plus 2n plus 1. And I'm trying to show that that is odd. So what am I going to have to do to show that that's odd? Pull out a 2 from the first 3 terms and leave this desirable plus 1 at the end that we want to meet our definition, right? We want to, in order for something to be an odd number, I need it to be 2 times some integer plus 1. So that plus 1 out there is nice. I leave that alone, and I just pull the 2 out of the first 3 terms. So I'll have a 2mn plus m plus n. Okay. And here we've got both addition and multiplication, so I'm just going to say because of the closure properties, of the set of integers, 2mn plus m plus n has to be an integer. If you want to list out that it's closed under addition and multiplication instead, you could. I sometimes just go for whatever's list writing. All right. Okay. Then, by definition, x, y is odd. Because we know that xy is written in the form 2 times an integer plus 1. Okay. And that's what we were hoping to prove, that xy is odd. As soon as we see that, we know we're done, and we've done enough. Okay, so if we went back and looked at these examples and said, okay, well, what are some clues, or if I look at a problem, how could I tell if I should use a direct proof or if I should use a proof by contrapositive? Okay, so this one, okay. Here, notice that the conclusion had something simpler than the hypothesis. So if you have something like something like an expression over here that's in terms of the conclusion, it's much easier if I put this one, if I know something about n, to help me figure out something about n squared, because this is a simpler expression than this one. So if you have that kind of thing where the conclusion seems to be a simpler statement than the hypothesis, you can switch them around. Of course, you have to negate them, but negating odd is not a hard thing to do. So that's a thing to look for. Here, when you have, okay, a negation of something, and this could be either in the conclusion or in the hypothesis, but where we have this, n squared is not divisible by 4. Okay, so that tends to be problematic. It's much easier to prove something that is divisible by 4 than something is not divisible by 4. So if you ever see kind of the negated of a simpler kind of statement, that's a good clue that you might want to use the contrapositive. Okay. And this one, where we have the conclusion being, you know, something or something, that's a little bit tricky to do, right? But if I take the negation of that, it turns it into an and. So when I assume that something and something, I assume that those both are true at the same time, and then I can work with those two facts to prove things. So those three things are a good idea that a contrapositive may be the way to go. So those are just some things to look for. Okay. So the other thing to look for is when you have a statement written with multiple hypotheses. So suppose we have a conditional statement like this. Hypothesis 1 and hypothesis 2 implies conclusion. So you have more than one statement as part of your hypothesis. Okay. Well, it turns out that this is logically equivalent to, okay, not C and hypothesis 1 implies not hypothesis 2. We're actually going to convince ourselves of this so that we know that we can use it. We'll go ahead and just use a truth table. So let's look at this first one. So this H1 and H2 implies C. And then this one, not C and H1 implies not H2. All right, so how many rows are we going to need in our truth table? 8. All right, so I'm just going to divide this up half, half, everything in half so I can get enough rows here. All right, so that should be enough. All right, we'll just do H is true, false, true, false. We'll alternate 1 for H1. Oops, true, false, true, false, true, false, true, false. Okay. Let's go over here and copy that over here. So H1, we're just alternating true, false, true, false. So true, false, true, false. Okay, and then H2, we'll let that be alternating 2. So that will be true, true, false, false, true, true, false, false. Sometimes my mouth goes faster than my pen, and then I start writing what my mouth is saying. Okay, and so then not H2 over here. Okay, it's just going to be the opposite of that. So that one's going to be false, false, true, true, false, false, true, true. If I say it slowly enough, I can write it correctly. Okay, and then our C is going to have to alternate 4, so that's going to be 4 trues followed by 4 falses. And then not C is going to be the opposite of that, so it's going to be 4 falses followed by 4 trues. All right. So the only place that the conjunction is true is when both of the propositions are true. So we're going to have a true here on that first line and down here. That looks like on the 5th line. All the rest of them are going to be false. And then for implication, what's the only time we get a false implication? True implies false. Okay, and so we have that here and nowhere else. All right, so everything else is true.
Wait.
Oh, there was another.
It's the one under the false.
This is false implies false, false implies false, false implies false.
Never mind, I was looking at the wrong.
This is true implies false. These are all false, and this one is true implies true. I think we're good. I think it's just this one spot is the only one I see. Okay, and then over here, this conjunction, the only time it's going to be true is when we have 2 trues, which is on the 5th and 7th lines, I believe, and I think everything else is false. And then the only time we'll get a false implication is when we have a true implies false. So here's a true implies false. This one is a true implies true. everything else has a false hypothesis, so everything else here is true. Okay. So we should be comparing these two, and sure enough, they are logically equivalent. Exactly the same. So why did we go through all of that, and why do we even care about that? Well, when we have multiple hypotheses, okay, notice that we can keep one of the hypotheses as part of our, as a hypothesis, and then we just add the not conclusion, and the other hypothesis can move to the other side. So this is logically equivalent to the original statement. Okay. And so when we want to do a proof by contrapositive, we can just assume that not the conclusion, and then keep one of the hypotheses, and then just conclude that what the other hypothesis is, well, the negation of the other hypothesis. Okay. And this carries over if we had like 4 hypotheses. Okay, we could then do not C, we could keep 3 of the hypotheses and just have our conclusion the negation of the other hypothesis that we didn't include over here. Okay. So that can come in handy when doing one of these proof by contrapositive. So it's only necessary to show that one of the hypotheses is false, assuming that all the rest of the hypotheses are true and the conclusion is false. So let's look at this example. So notice we have if x is an even integer and y squared is an odd integer. So we do have indeed, this is like our hypothesis number 1. And then we have and this one is our hypothesis number 2. And then this here is an odd integer, that's our conclusion. So essentially we have 2 options if we're doing a proof by contrapositive. Okay, so we can start with, okay, not C, so x plus y is even. And keep the first hypothesis, so x is even. And then imply not the second hypothesis, so that would be y squared is even. So that's option number 1. And option number 2 is to do the negation of the conclusion, which is x plus y is even. And instead of keeping the first hypothesis, keep the second hypothesis. So we would go with y squared is odd, and then conclude the negation of the other hypothesis that we didn't keep. So that would be this one, that x is odd. So either one of those would be fine. Okay. How many people vote for option number 1? How many people vote for option number 2? 1. Okay, so it's 3 to 1. I like the even one as well. Even is just easier to work with. I like even. And there's lots of abstains I see. So you don't feel very strongly about this apparently. That's all right. Okay, we're going to go with option number 1 because 3 of us really desired to do that. Okay, so we're going to use a proof by contrapositive. So we will proceed using a proof by contrapositive. And this one you really need to tell the reader what you're doing because, you know, this one, so in particular, we will show that if, and then we're going with option number 1, Oops. That was the, if I haven't stopped yet, we need to stop soon. Okay, I'm just going to write what we're going to show and then we'll keep it for next time, but I have to finish the sentence. We can't stop mid-sentence. So what we're going to show is that if x plus y is even and x is even, then y squared is even. Okay, so that's the trickiest part of this proof, is just getting that sentence down. And now it's just a direct proof of that. Okay. All right, somebody probably does want to get the lights because I doubt you want to take your quiz in the dark.